All right, welcome to this video about dynamic programming, coding interview tutorial where we talk about algorithms. So in this video, what we're going to discuss is what dynamic programming is, when to use it, especially during your interview, where it is used in the real world, and how it is used by completing a famous dynamic programming question called the 0-1 knapsack problem that shows how to use tabulation, or aka a bottom-up approach. So we'll discuss all this further, but first, let's all get on the same page here. So let's talk about first, what is dynamic programming? Dynamic programming, or DP, which is how I'm going to refer to it throughout this tutorial. So DP is a technique utilizing guessing, recursion, and memoization, or aka memory, to design new algorithms used for optimization. Optimization is all about efficiency. So in DP, we try to minimize the time complexity without too much regard of disk space and memory. Just think optimization. All you got to do is think about optimization when you think about dynamic programming. I think semantics in all things computer science can sometimes initiate some confusion. Trying to find the meaning and understanding from a name or title doesn't always help. And in this case, Richard Bellman named dynamic programming to conceal the mathematics involved and to make it sort of sound impressive to government officials. You'd be surprised when you find out the reasons for designating certain titles in computer science. So let's just think optimization here. So within these interview questions, you're going to see some keywords, some terms that deal with optimization. So shortest, longest, minimum, maximum, least, most. Chances are you're going to be using some sort of dynamic programming. So where is it used? Dynamic programming is powerful and is found in every industry, everywhere. Some examples of this are the shortest paths, minimum length, in machine learning and artificial intelligence through backpropagation, in networking to transfer data from a sender to a receiver in a sequential manner, image processing, bioinformatics, security. It's really everywhere. So when can you use DP? When can you use dynamic programming? There is a certain criteria needed to be met. If you're familiar with the graph theory, recursion trees and DAGs and all that good stuff, remember a problem must have a topological order and be acyclical. So a topological order and acyclical. If you're not familiar with graph theory, in other words, we can say that the question must have two things, meet these two criteria: overlapping subproblems, where the same algorithm recursively solves the same problem, and two, an optimal solution. This means that the overall solution to the question can be found by using a combination of the solutions to its subproblems. So the optimal or best solution of the subproblems are going to all be combined to find the optimal or best solution of the original question, or the global question. So you might ask yourself, how is this any different from divide and conquer? If you're familiar with divide and conquer works by dividing a question or a problem into subproblems and conquering and solving each of those subproblems. The subproblem solutions will later be combined to reach the solution to the original problem. And that sounds exactly the same, right? Well, dynamic programming really is just an extension of divide and conquer. What makes it different is that it uses memoization and tabulation to store results, decreasing the time complexity. So optimization. We'll talk about these two here. So let's take a look at these two approaches to dynamic programming: tabulation and memoization. So tabulation, which means you put the info, any sort of information into a table. That's what tabulation means. And memoization means to remember, to use memory to remember something. So tabulation has to look through the entire search space, requires careful ordering of subproblems, where memoization doesn't have to do this stuff as much. Memoization is a little slower and tabulation is a little faster. But ultimately, it all comes down to the subproblems. If all the subproblems need to be solved at least once, tabulation or a bottom up approach outperforms memoization, which is the top down approach. And this leads us to our problem here. So remember, tabulation, bottom up approach, memoization, top down approach. So let's go to our knapsack problem here. I chose this question because dynamic programming, which appears everywhere, this will appear often in interviews and in the real world. When you want to maximize the resources available with constraining amount of space, you're definitely going to be using some sort of dynamic programming. So the famous question reads, write a program that selects a subset of items that has a maximum value and satisfies the capacity weight constraint. All items have integer weights and values. You cannot split an item, hence name the 0, 1 or 1, 0 knapsack problem. There will be no fractions involved. And what they want is for your function to return the value of the subset. So we have a backpack to fill. We want to fill it with the most value, thinking about the constraint of the weight that we have. So while reading this question, a few things stand out for me that suggest we utilize some dynamic programming. First, we kind of find a key word here, maximum. Keyword right there says, oh, this is going to be a optimization problem. The second, I see that it mentions subsets of items, which suggests to me subproblems and the use of divide and conquer. So let's see if we can satisfy the criteria for dynamic programming here. Let's talk about the optimal solution. Smaller subproblems to solve the larger global problem. Optimal solution, we can use a recursive function here to solve this problem, but we want an optimized solution to the problem. So a naive recursive function isn't going to work. It's just going to give us a big O, a long big O with exponential time. What we want is polynomial time, and that's just a fancy way of saying slower to faster. So faster polynomial time. And two, we're looking at the overlapping subproblems here. We do have these. The easiest way to see this is by the use of a table. Now, deciding on which approach leaves me with the thought that all subproblems must be solved. Each and every combination of items and value needs to be calculated, so a bottom-up approach will be conducted. Let's use some tabulation to get an understanding of how the program will work. Get a pen and paper and follow along, because this is where it's going to get a little confusing. I suggest you write it down, watch this part of the video multiple times, and try a problem that you made up. There's a problem here that I'm not going to use on this slide here. So here in this knapsack, you have a weight capacity constraint of 15 kilograms. You have a few items here that have these kilograms and values associated with it. So go ahead and try that one on your own. But on this one, I'm going to give you the data. I'll walk through it with you, and we'll get a good understanding of this tabulation approach, this bottom-up approach. Once you understand the tabulation approach and how the table operates, you'll be able to apply this in almost every dynamic programming approach. And it will help you not only with the interview question, but also in the real world. Okay, our info comes in two arrays. We have weight in kilograms, and then we have value in dollars. The capacity of our knapsack is going to be 8 kilograms. So essentially we have 4 different items, and we have a capacity of 8 kilograms in our backpack. And we want to fill our backpack to get the most value from this backpack. So let's see what this table is made out of. The columns, let's start with the columns first. The columns are our weight capacity constraints. We start from 0 and we end with our maximum weight capacity constraint of 8. We break up the capacity because we will be using subproblem solutions to calculate the global problem solution. Now let's look at the rows here. The margin on the left contains the item number and the data associated with that item. I like it in a tuple form, and make a key in this space so you don't get confused with the order of the tuple. Each row includes the item above. So each row here will include the item above. So for item 2 here, we're going to include item 1 and item 0 when we solve our sub-problems here. So each one of these cells here is a sub-problem. And with each sub-problem, we want to figure out iteratively what our value and weight will be if the item is chosen or if it's not chosen. I included these 0 values here in this first column and this 0 value here in this first row because this is how your array is going to be created in your program. So for item 0, we're not going to have any item. So let's just go ahead and fill this first row in with all zeros. That means we have zero items. Now let's fill out the first 2 rows and see what algorithm we can use recursively. For the first cell in the first row, so the first cell in this first row here, for item 1, we're solving the sub-problem that states if we had a weight capacity of 0, so here's our weight capacity. If we had a weight capacity of 0, can we use the first item? Can we fill our knapsack with the first item? Of course not, because our weight capacity is 0. Okay, that's how we solve that sub-problem. So let's look at the next cell here. So this cell sub-problem asks, if we had a weight capacity of 1, what value can I fill the knapsack with? Again, we have a weight capacity of 1. Well, in the tuple here, don't forget the weight in kilograms comes first. So the weight of this item here for item 1 is 3. So obviously, we don't have any capacity to include that item inside our knapsack. And of course, when it comes to 2 kilograms as well, we do not have enough capacity to fit item 1. The next cell for item 1, let's start with this one here. We have a weight capacity of 3 kilograms. So 3 kilograms, which means we can fill this knapsack with item 1. So the value, which is the second value here, the second number in this tuple, is 2. So we're going to go ahead and fill in the value within that cell. Since there are no items in the row above, we can say that filling our pack with just item 1 will give us a value of $2. The next cell for item 1, we're not including any other items here. We're not including any other items in our knapsack. We are only taking item 1. So our value will remain $2 throughout the rest of this row. So a value of $2 is given when we fill our knapsack with item 1. So after the first row, we've answered 8 subproblems. So 8 of these subproblems we've answered. Now in the next row, we will use these 8 questions or these 8 solutions to further our progression to the global optimal solution. Now the first 3 cells of our second row. The first 3 cells of our second row have a weight capacity that doesn't allow us to bring any items. So for the value, we will input a 0 into these cells. So with a weight capacity of 0, we can't fit a 4 kilogram item in there, nor can we fit a 3 kilogram item in there. So all the way up to our 3 kilogram capacity, we will include some zeros. Now, upon arriving at the weight capacity of 3, so now we have a weight capacity of 3 kilograms. We have to remember that we can include item 1, and therefore we take its value from above. So with a weight capacity of 3, we're not able to fit item 2 into our knapsack. Item 2 weighs 4 kilograms. However, we are able to fit item 1 in our knapsack. Remember, each row includes the items above it. So therefore, at a weight capacity of 3 kilograms, we can have a total value of $2. Now the reason we choose from above is because the choice we made does not take away from our weight capacity and only takes the value of the item or items above. So in other words, at a weight capacity of 3 kilograms, we are unable to take item 2. However, we can take item 1, which allows us to gain a value of $2. So now this next subproblem here, this next cell, is when things get interesting. We now have a weight capacity of 4 kilograms. The subproblem again is asking, with a weight capacity of 4 kilograms, would item 1 or item 2 bring the most value? So let's look at item 1 here. We have 3 kilograms with a value of $2, and item 2 is 4 kilograms with a value of $3. Well, item 1's value is less than item 2's value. Therefore, we will choose to fill our knapsack with item 2. So the value here in dollars is going to be 3. So in other words, we just chose the maximum value of item 1 and item 2 while taking into account the weight capacity constraints. Each cell thereafter uses the same exact subproblem each time. So let's make some pseudocode representing each subproblem for each cell. So down here in the green we have a max. We're trying to find the max value. The max value. The max value between items while accounting for the weight. So we could show it like this. So if we take the value of the current, so let's say we were on item 2 here, we take the value of the current item, add the value of the previous item, and then subtract the weight. Gives us our first value to choose from. The second value to choose from is just the value of the previous item. Let me explain this a little further. On our next cell, our weight capacity is 5. So let us use our pseudocode to help show how this is being calculated. So with the capacity of 5, the available items of item 1 and 2. Let's fill this into our pseudocode. We select the maximum value of the current value. So the current value here would be 3. So here we want to find the max value of 3 plus, so our current value plus the value of the previous. Select the current value of 3 plus the value of the previous. So we want to point to row 1. So here we take the value of the current, which is 3, and then we have to count backwards because we are including the weight here. So at 5 kilograms as our capacity, keep in mind, we have 4 kilograms for our item number 2. So what we do is we point to item 1, so we point to the row of item 1, and we count back 4 spaces. 1, 2, 3, 4. Our value here is 0. This gives us our first value of our max function. Next, we check the value of the previous. And to check the value of the previous, all we do is refer to the number that is above. So 2. So as it's simplified, we have a max function, and we want to choose the value of 3 and 2. Of course, the max is going to be 3, and therefore we can throw that in the cell there. Okay, we choose our next cell. Right, we're still on item 2. Now we have a weight capacity of 6 kilograms. So we have 4 kilograms for item 2. So now we have a weight capacity of 6 kilograms. Keep in mind, item 2 has 4 kilograms of weight, and item 1 has 3 kilograms of weight. So again, we're probably not going to be able to fit item 1 in our knapsack. But let's do this algorithmically, as we were doing with our recursive function here. So if we refer to the above row and we count back 4 spaces, 1, 2, 3, 4, we have a 0. So our max function in our pseudocode, 3 plus 0, and then we refer to the value above for our previous value, 2. Again, we have a maximum of 3. Okay, now things will get interesting again here, because now with a weight capacity of 7 kilograms, now we're able to fit item 1 and 2. So let's see how this will work. So we refer to this cell, and let's write this into our function so we don't forget. So we have a value of the current, which is 3. Now we're going to find the value of the previous. So we refer to the row above, and we're going to count the weight. We're going to count the weight because we're subtracting the weight here. So we're going to count the weight by 4. 1, 2, 3, 4. Our value is 2. So we're going to add 2 for the previous value. The next value in our max function is the value of the previous, and we can find that by referring to the number above, which is 2. So here we have a max function where we want the maximum of 5 or 2. 5, of course, is our max, and therefore our value is going to be 5. All right, moving along. We start in this cell. The value of our current item, I'll write the max function here. The value of our current item is 3. In order to find the value of the next item, we're going to refer to the row above, subtract 4. 1, 2, 3, 4. We're accounting by the weight when we subtract. So our value here is going to be 2. And the value of the previous, we're going to refer to the row above, 2. Again, our max will be 5. All right, moving down to item 3. Now we're moving down to item 3, so keep in mind that item 2 and item 1 will be accounted for in this sub-problem as well. Now, with 0 weight capacity, we know we're not going to get any items in there. We know we're not going to get any items in a 1 kilogram or 2 kilogram weight capacity. However, we can still fit an item in the 3 kilogram weight capacity. And in order to do this, we refer to a previous value, where the previous value here will be 2. Next cell, we have a value of 1. The current value here, the current value of item 3 will be 1. We're going to add that with the previous. So let's find out what the previous is. So if we refer to the top here, and we're going to subtract 6. We're going to subtract 6 here, and we're going to run out. So it's going to be 0. Value of the previous is going to be 0 here. Of course, you can't fit item 3 into item 4. But let's just see how this looks in our max function for now. So this is the value of the current, value of the previous. Now let's look at the value of the previous. We're going to look above. It's 3. Max value here is 3. So we're just going to take the value of the previous. Again, we're going to have the same outcome for a 5 kilogram weight capacity. Let's just take the value of the previous because we know item 3 will not fit into this weight capacity. Item 3 will not fit into our knapsack because of that weight capacity. So here we're able to fit it in here. So let's see what will work here. Using our pseudocode, let's take the value of the current. The value of the current is 1. We're going to add that to the value of the previous. So let's refer to the top row. We're going to subtract 6 because the weight on item 3 is 6. So 1, 2, 3, 4, 5, 6. Value here is going to be 0. And the next value we need in our max function is the value of the previous. And we get this by referring to the number on the top. Here is 3. So the max here will be 3. All right, let's do this again for a weight capacity of 7. Starting with the value of the current, we're going to add the current value with the value of the previous. So to find the value of the previous, we will return up 1 and back 6 because of the weight of 6 kilograms. 1, 2, 3, 4, 5, 6. Okay. We've got the first part of our function. The second value of our function is the value of the previous, and we get this again by referring to the number above, 5. Of course, 5 will be our max. Okay, with a capacity of 8, almost there, we're solving all these sub-problems. And it will lead us to that optimized global solution. Now with a weight capacity of 8 kilograms, we have a current value of 1. We're going to add that with the previous value. So let's come up here and let's go back 6. 1, 2, 3, 4, 5, 6. 1 plus 0 is our first value in our function. Then we get the value of the previous by looking above and seeing that 5 is the maximum value here. All right, last row, we're almost there. Item 4. Item 4 has a weight of 5 kilograms and a value of $4. Of course, we know that in any weight capacity below 3, we're not going to be able to fit any item. So let's go ahead and mark our zeros here. The weight capacity of 3, we could do this algorithm, but I already know that nothing else is going to fit into our knapsack other than item 1. So I just want the previous value, so I'm going to look above. I'll find the previous value. The previous value here will be 2. Next cell, again, I know that item 4 is not going to fit. Item 3 is not going to fit. I just want the previous value because I know item 1 or item 2 will fit. So let's look at the previous value. The previous value here is going to be 3. Okay, here, item 4 does have a possibility of fitting into our knapsack. So let's see here what we can do to find out what will be our max. So let's take the value of the current. The value of the current here will be 4. I'm going to add a marker here. 4. We're going to add that to the previous version. So again, to find the previous version, refer to the row above and count. We have 5 kilograms of weight, so we're going to count back. 1, 2, 3, 4, 5, 0. And then the previous value, which is the value above, is 3. Our previous value is 3. We take the value above. So the max between 4 and 3, it will be 4. Okay, last 3. So let's take the value of the current. The value of the current is 4. All right, we want to find the value of the previous, so we're going to refer to the row above. We're going to subtract that weight off of there. 1, 2, 3, 4, 5. We're going to add 0 to this. Our previous value, remember our previous value is just the value above, and 3. The max between 4 and 3 will be 4. Okay, last 2. Let's take the current value of 4. We're going to add that to the previous value. Refer to the row above. We're counting back because we're subtracting the weight, counting back by 5. 1, 2, 3, 4, 5. 4 and 0 is our first value of the function. Now we want the value of the previous. So here the previous is 5. And 5 is the max between those two numbers. Okay, last one. We take the value, the current value of item 4, which is $4. We're going to add the value of the previous. So refer to the row above, count back 5 for 5 kilograms, accounting for weight. 1, 2, 3, 4, 5. Here we have a 2. All right, that gives us our first value in the function. Now, a value of the previous, we refer to the number above. And that number above is 5. So 4 plus 2 is 6. And 5 is our other number. So the max of this is 6. Programming works. And this is what the sub problems are going to break down to. Now, we found that the max value that we can put in a knapsack is going to be $6. So $6 here is going to be our max value. And that's what they wanted us to return in the question. Now, another question that you might get asked during your interview after maybe filling out a table like this would be, well, with this max value of $6, what items were chosen to fill your knapsack, right? So one way that we could do this is by going backwards through the sub-problems to find out which items were chosen. So what we're going to do is we're going to go to the max value here, this 6. And remember, the value of the previous, right, the previous item, right, is above. So we're going to look above here. Now, if those two values don't match, then we know that, oh, we've chosen item 4. We've chosen item 4 because the previous value didn't carry down. The previous value didn't carry down. So here, in this subproblem, we've chosen item 4. So now to work backwards, we're going to go one row up, right? And we're going to subtract the weight of 5 again. So 1, 2, 3, 4, 5. And now we're going to check to see if those values are the same. 2 and 2. 2 and 2, they're the same. So that means that we didn't include the value here for item 3. We didn't include item 3 into our knapsack. So we're going to go back up to this now, and we're going to check again. We're going to check again to see if these values are the same. And these are the same. So that means that this item was just carried down from the previous. Remember, because the previous item carries down. So now we can see that we're back at item 1 here. So now at item 1, we're going to check the previous row. Here is item 0, but we know that well, there's only one more to choose from, and those values are different, of course. So that means that we definitely did choose item 1. So to answer this question, item 1 with a value of 2 and item 4 with a value of 4 gave you your total value of 6. So 2 items that you chose to include in your knapsack include item 1, and item 4. The last part, we're going to review the code involved to find the solution of our 0 to 1 knapsack problem. I'm going to use a website to display the code called Python Tutor. When I was first learning code, this website was instrumental to my progress in C, use it in Python and JavaScript. And you can write the code in your browser and see it visualized step by step, which is great. They even have a section where you can get live help from others and get help. Or you can give live help, and then you can get live help from others in real time as well. So it's cool if you want to check that out. All right, so now that we know how the table works to find the subproblem solutions and how the subproblem solutions combine to give us our global solution, I'd recommend writing out some pseudocode to give you a template to use while defining your function. And I'm not going to lie, this problem was a difficult one. But before you check out the code, I do encourage you to try it out on your own first. I wrote some code and then reviewed it with some code I found online and compared the two. And I chose to show you the code that I found online. It's succinct, it's easy to read, and can help you really define your function a little bit easier than the code that I wrote. Here it is. It's commented out with many lines too to show you exactly what we're doing in each line. And I was also trying to be as explicit as I could in the naming of those variables to avoid any confusion. You can name your variables however you want. You can check out the code on GitHub in the link within the description as well. So without further ado, let's check this out here. So we're going to use the same numbers that we used in the table that we created. It's a capacity of 8. We have the value. Remember, this is all caps because it's an unchangeable variable. PEP8 might be good to use. All right, so we define our function. We'll put in our 4 parameters here. The number of items, you could just take the length of either the value or the weight array, and it'll give you the number of items that you're going to use. All right, so the first thing we have to do is build an empty 2D array that will be used as the table, right? So if you are familiar on how these 2D tables work, you always get the rows and then the columns. So we went ahead and built a 2D array, all zeros. Yeah, nothing too complicated there. It's a nice list comprehension, makes it easy to read. So the second, we're going to fill the table with the calculations. Now, for each, let's say this first for loop, right? Because everything goes by rows and then columns. So for the for loop here, for each row in the table, this is for item 0 and through item 4, if you remember from the table. And the columns, remember the columns, we had the weight capacities on the top. Now we have our conditional statements here. We have 3 conditional statements. If the item 0 or the weight 0, of course, we want to keep it 0. We don't want to change that. If you remember the first row with all the zeros for item 0, and if you remember the weight capacity of 0, 1, and 2 kilograms, we weren't able to fit anything in there. So we're not going to play around with that too much. This is also the reason why you see these plus ones and minus ones and things like that, because you have to remember when you're programming, it always starts at 0. So that's something to attend to. But you've probably been programming long enough to remember that. All right, so we have our 3 conditional statements. And of course, it's just going to return the max value obtainable. Let's visualize this execution. This is why I like this program here. We're able to see exactly what's going on now. So 278 steps. It's just like having a breakpoint on each step, right? So the first part of this, we're just going to load up all these variables here. We have value, weight, capacity, number of items. Load those up. So now we have the pointer pointing to those values and arrays. Now we have a function defined. Now we have the function defined, and it will start running through our function here. So if you look, it's going to start first. We're going to start to build the table first. Okay, I'm going to sort of rush through this to show you how it's building the table just by the rows and columns, all zeros. Remember, you can see this this red arrow. The red arrow is the current step that you're on. The green arrow is the previous step that you're on. Building our table, we rush through those steps. Comes out with a nice 2D table for us. Okay, this is why I wanted to use this site, because I wanted to show you how these two for loops are going to fill in this table that we've made, this 2D array. So we're going to fill the table with these calculations, and I want you to watch this red arrow here, because this red arrow is going to indicate which step that we're on. If you remember from the table, we have item 0. This is going to be item 1, item 2, item 3, and item 4. Right? So, of course, when we first start to go through our table, when we first start this for loop, of course, it's going to do item 0, and it's going to be all 0. So it's really just going to go to this first conditional here. We'll watch it go through. Okay, now it's on item 1. So now on item 1, here we can see which item it is, and here we can see what the weight of capacity is going to be. So we have 0 kilograms. Of course, it's going to be 0. A weight capacity of 1 kilogram, of course, it's going to be 0 again. And for a weight capacity of 2 kilograms, it's going to be 0 again. But when we get to 3 kilograms, move this up just a little bit. When we get to 3 kilograms, we'll see that this conditional statement is going to start to execute. We take the max value, and the max value in this case will be that 2, and that's how it's going to input. So watch that arrow and watch how it fills in this table with these conditional statements. Okay, so after it's run through these 2 for loops, we'll move on to this next part of the function, which is the return statement. And we're going to return that max capacity, or that maximum value there. Okay, we made a little print statement for it. $6 is the maximum obtainable value. All right, so if you want to check out this code, I just thought that would be a pretty good indication of how these 3 conditional statements are working with these 2 for loops here to fill in those values just like we did manually. So I hope I cleared some things up for you in dynamic programming, and I hope I cleared things up for you in the knapsack problem. It's a complex one, it's difficult, but when you break things down all the way, build them back up, persevere, you'll get it. Keep going. Thanks for sticking with me.